Afternoon, everyone, and welcome to Dynamic Lighting and Cannabis Cultivation Strategies that Work. My name's Tim Kopp. I'm with the Fluence marketing team, and I'll be moderating today's session. Joining me today are Dr. David Hawley, Principal Scientist at Fluence, and Plant Specialist Dr. Sabrina Carvalho. With their wealth of knowledge and experience in this session, Dave and Sabrina will be discussing how adjusting spectrum and intensities at the proper times and in the right ways can open up new opportunities in cultivation. We'll be leaving some time at the end for answering questions, so I invite you to ask any questions using the Q&A button that you should see at the top of your screen. We have a lot to cover today, so with that, I'll turn it over to Dr. Dave to get us started. Dave.
Thanks, Tim, and good afternoon, everyone. Indeed, my name is Dave, and the presentation today is intended to give you an overview of kind of the main research questions we've asked in cannabis that would inform a dynamic lighting solution, ultimately concluding with what we've seen that works and what we think has commercial relevance and could be impactful to your business today. The latter half of this is going to be focused more on that research. I'm not going to be diving into the specific details of every single study in the presentation, but of course we have that. So if there's something that jumps out to you that you want to know more about, please don't hesitate to get in touch. The latter half of this presentation, Sabrina will be speaking on a new technology that we are going to have in the market very, very soon that I think is going to be interesting to a lot of people. So without further ado, let's get into it. Dynamic lighting. I like to contextualize this topic by talking about why dynamic lighting is a thing that we all aspire to. I mean, even in my days of grad school, being very naive, thinking I was going to figure out the perfect lighting for all applications all the time, that enthusiasm was always part of a broader narrative where one day, whatever the crop, cannabis, lettuce, tomato, you name it, we would have these perfect systems where you could just stick your plant in and say, tomato, please, and it just does it. And you get these big, beautiful tomatoes that have great flavor, or cannabis that has a really dense inflorescence morphology, or optimized chemistry, or whatever it is that you are after, it could just do it. Maybe I grew up watching too much Star Trek, but I like to believe that that sort of technology is in the future. Lighting is a key part of this. And as you, I'm sure, know, lighting has the power to do an awful lot with plants, right? Using the right light, you can steer things like yield, you can steer morphology, you can steer chemistry. It is a very creative tool in that way. Similarly, light can also be a very destructive tool in ways that are favorable for you if used appropriately. So, for instance, certain wavelengths of UV can destroy superficial pathogens. There's research out there that says if you use the right combination of blue and UV, like UVB, UVA, and so on, you can also induce systemic acquired responses in plants that essentially increase their hardiness over time, thus making them a more robust crop in the long run and potentially making them hardier to environmental changes. Anyway, the thing is, light as a part of this broader system is really impactful and really a great tool. But as you know, lighting isn't free, right? It's just energy. It's just a different form of energy that we have to pay for and repackage and then deliver to the plant in a different way. And it's actually really nice to be speaking to mostly an audience on the eastern side of the Atlantic today, because I know this audience in particular knows what it's like to pay higher energy prices than you really need to. And so you really need to ask yourself that question for every lighting decision you make, or HVAC question, or nutrient question, or whatever else. You need to ask that question: does this make sense? Is there a good ROI for what I'm doing here? And that's certainly the language that we speak in this presentation. So enough said about that. The idea that you could automate light and have this dynamic lighting system and dynamic environments and everything sounds really cool. And again, probably with this audience, you guys know this isn't just ideas of science fiction, right? This sort of autonomous greenhouse is something that you see at Vogniken Research, for instance, where every year they had the Autonomous Greenhouse Challenge, where, if I understand correctly, the last couple of years, an AI system that was growing tomatoes outperformed growers in the area, albeit at higher energy costs. So there's still clearly some optimization to do. But the fact is, these AI systems are getting really, really good at growing certain crops. Now, the thing about this is that, pardon me, as you know, right, tomato or cucumber or strawberry are very, very well defined. So for instance, if you're growing tomato, you're probably growing a cultivar called Marlies. If you're growing strawberry, you're probably growing a cultivar called Albion, albeit that's slightly different genetics than we do in Europe versus North America. But the point is there's very, very well established cultivars with stable genetics out there that everyone knows how to grow, right? The methodology for tomato or strawberry or cucumber or lettuce has been so well defined through decades, if not centuries of research at this point that say space your plants like this, prune like this, harvest at this time, use this nutrient recipe, use this lighting strategy. Cannabis doesn't have any of that. Cannabis has ridiculous genetic diversity. It's just such an immature um, species by comparison for commercial horticultural production. Similarly, the cultivation practices vary wildly. If you ask someone in Europe versus North America versus even just within North America, the West Coast versus East Coast, people grow really differently. And that means that making the crop models that are required for autonomous production have a long, long way to go. And this next slide, I just illustrate that, right? Here's 8 different cultivars. And again, we can see just how different these all are, even within a single cultivar, like Blue Dream, for instance. The one that I grow is going to be very different than the Blue Dream that someone is growing on the other side of the planet or even just down the street from me. So it's really, really hard to develop these autonomous crop models that theoretically a truly dynamic and automated smart lighting solution would fit into. Nonetheless, over the last few years, we have identified some lighting strategies that we see are highly conserved in how they affect cannabis across many, many cultivars, right? And that's something I want to emphasize right now, just as we get into the research section of this presentation. In fact, let me throw these thought bubbles on screen. There are lots of questions that people have asked about cannabis. Can UVB enhance potency? What about blue? Does it do the same thing? What about ramping PPFD to emulate sunrise and sunset? Or more broadly, just do I need far red and can I trigger the Emerson enhancement effect? And should I be caring about PAR or EPAR? We have answers for a lot of these, but what I want to give you is the caveat that there are always exceptions, right? And so what we try to do at Fluence with our research program is we try to ask a lot of these questions either in the same or slightly different ways across several cultivars and several cultivation strategies so that we can give you a more, what we think is a more robust kind of holistic answer where we say, in general, far red does this. In general, blue does this. In general, you can do this with ramping or not. And that's really important to kind of handle because if you only do a single study on a single cultivar, you may find an outlier that says, in this particular case, far red does this or UV does this, right? But I know that those single studies really aren't that impactful to the commercial grower because you will rightly say, well, yeah, that happened in your lab with what you're growing the way you do it. That doesn't matter to my business. No, let me emphasize. We do this research in a way where we do try to make it as broadly applicable as possible. And again, I'm not going to be speaking to the exceptions to the rule, but more so the holistic conclusions that we've seen. All right, so I want to start basically with the short wavelengths here. I'm going to start by talking about UV, and in particular UVB. For a long time, there's been a perception in the world of commercial cannabis production that you could amplify secondary metabolite production through doses of UVB. And most of our clients, when they're asking about UVB, would say, should I be deploying UVB during flower to increase secondary metabolism? And the short answer is simply no. The way that we did our study was that we had a single intensity of UV that we applied for different durations, therefore giving you different integrals of energy that we applied to the plants. And essentially what we saw was that the more UV that we applied, and for longer, the worse the plants were. So yield went down, chemistry, as far as cannabinoids and terpene concentrations went down, and the crops obviously look pretty unhappy. And that's what you see in the picture on the right. You get these leaves that have canoed and kind of curled back on themselves because they're just trying to, it's like they're doing this. They're just trying to say, no, I don't want to be exposed to the light. A very telling sort of morphological response. But suffice to say, that sort of simplistic application of UVB really didn't do what we had hoped. For what it's worth, that's not the same as me saying UV has no place in cannabis cultivation ever. I think there is opportunity for more research, particularly if we do some sort of like earlier application during veg. We don't have research on that yet, But hypothetically, we think, well, maybe we can induce a kind of systemic hardening, like I talked about before. So still a very interesting area of research, but right now it's not something that we would recommend people use commercially at all. Um, Basically, moving on to a slightly longer wavelength is blue light. And the question often comes, can I induce an upregulation in secondary metabolism or favorable morphological changes in cannabis by using blue? And this is intriguing me because it's a slightly lower energy photon than UV that would theoretically do something similar. And that's good because, for one, the diodes are much more robust. They're going to last longer and they're cheaper. But two, they're also much safer to be around. You can be in blue light basically indefinitely and not have any kind of health risks, whereas with UV, you have risks to your vision and your skin, and potentially there are cancer risks as well. So for a lot of reasons, blue is intriguing as a tool. Um, the idea that blue in particular could induce a greater sort of secondary metabolite profile is something that is proven, albeit in other species, right? So you may know about how you can increase anthocyanin production in species like lettuce, right? So you have green leaf lettuce and red leaf lettuce. That red leaf lettuce is producing a compound called anthocyanin, which is a secondary metabolite. So you might say, well, blue light increases secondary metabolites in lettuce. Maybe it does the same thing in cannabis. Totally reasonable thought process. I had the same thing kind of cross my mind a few years ago. But the punchline is that we haven't really seen blue light increase secondary metabolism as far as cannabinoids and terpenes go. Um, and now that we've taken kind of a deeper look at the biochemical processes, it's a little bit easier to understand why that is. So we're going to go a little bit deep into biochem here, but just bear with me. I think it's worth understanding this so that you can make a more informed lighting decision in the future. So when we look at a high-level view of plant metabolism, it starts here, right? With light and carbon dioxide and water, metabolic processes happen to make sugar. That sugar is then metabolized to make photosynthetic pigments and other light receptors, or it can make some antioxidant pigments and some abiotic defense compounds, or in the case of cannabis, it can make some cannabinoids, terpenes, and some other photosynthetic pigments. So I'm going to show you the same information again, but now one layer a little bit deeper. Okay, so when we talk about photosynthesis, there's really the light reactions of photosynthesis, then the dark reactions, and then glycolysis. And glycolysis, right, this is actually a pathway common between plants and animals, and it's metabolic really important. It's kind of like this is where all the building blocks begin to then make everything else that the living organism needs. So we're going to dive into glycolysis and actually even a little bit deeper in just a second. But anyway, from glycolysis, you can go down this pathway and you can produce things like chlorophyll and phytochrome. So two compounds that are very, very important in interactions with light. You also have things like ethylene, which is a plant hormone involved in ripening. Or you can go to the left here via the shikimate pathway, and you can produce hormones like salicylic acid and auxin involved in rooting and shoot development, respectively. And you can go down to produce flavonoids and anthocyanins, like the purple pigment I described in lettuce a moment ago. And again, that's going to be important. We're going to look at how that's regulated in just a second. And then lastly, you can go to the right here. You can go through the DXP pathway or the mevalonate or MVA pathway. Both of these pathways yield things called isoprenes, which are just like little 5-carbon chains that come together to make your terpenes. They're really small, really lightweight molecules. That's what allows them to volatilize and reach our olfactory senses, and we can smell and perceive these things. But terpenes, in this pathway, you get, again, gibberellins. This is basically another plant hormone that increases plant metabolism overall. You can produce cannabinoids, and you can produce carotenoids, xanthophylls, and abscisic acid. And that whole chain is involved in mitigating light stress, essentially. So like I said, I want to illustrate how the paths to the left here via the shikimate pathway and the paths to the right are differently regulated. So to do that, we need to take one deeper look, focusing in the middle on glycolysis there. So let's zoom in one more time and look at glycolysis. Yeah, these are the paths I want to illustrate. Sorry. So if we look at glycolysis, we can see here that there are a few different steps here. We go from glucose to glucose 6-phosphate to glyceraldehyde 3-phosphate, phosphenolpyruvate to pyruvate to acetyl-CoA. And you'll notice that the intermediates in this chain are utilized differently. So if we look to the left here, highlighted in blue, you see glucose 6-phosphate and phosphenolpyruvate. These are the two intermediates that are consumed via the shikimate metabolic process. And these are the two immediates that go on to make your flavonoids and anthocyanins, and therefore that red pigment that you see in blueberries and in lettuce and in grapes and so on. Whereas basically the ones that are left over, glyceraldehyde 3-phosphate, pyruvate, and acetyl-CoA in orange, those are the ones that go off to the right and make your cannabinoids and terpenes and are pretty clearly differentially regulated. So let me just make sure. There we go. I want to emphasize here that this pathway to the left is very well characterized and understood. So we know that the shikimate pathway, in particular the synthesis of anthocyanins, is strongly regulated by blue light. Blue light through sort of a signal cascade with transcription factors and so on induces the metabolism of an enzyme called chalcone synthase. And chalcone synthase is kind of the gatekeeper in this process to make chalcone that ultimately then goes on to make these pigments. That's a very, very different thing. It's a very different regulatory mechanism than what's going on the right here. So I have this picture of the cucumber, not the cucumber, the caterpillar. Sometimes English is hard, even for me, even though it's the only language I speak, to my shame. Anyway, we have this caterpillar here, and I've illustrated this caterpillar because this pathway to the right is strongly regulated by mechanical damage to the plant, like things like herbivory. So whenever I give this presentation, I make the joke that, if you want to upregulate terpenes and cannabinoids, you might actually be better off throwing a bunch of caterpillars on your plant. But to be clear, I'm not saying you should actually do that. I'm just saying it might be an interesting experiment. Anyway, point being, these two pathways are quite divergent from each other. So just because they are both secondary metabolite pathways, being able to regulate one branch of this with blue light is not the same as being able to regulate the whole thing with blue light. Okay, secondary metabolism aside, the other question that we get about blue is, can it make a more compact canopy? And truthfully, what we've seen is that during flower, if we apply more blue during flower, we don't see a huge difference in canopy architecture. If we apply more blue during veg, by way of either like a white light versus a pink light, again, the differences in canopy architecture, like branching and plant height, are marginal at best. So we continue to explore opportunities with blue light. We think that if we apply it earlier and earlier, when the plants are younger and a little bit more morphologically plastic, maybe there's an opportunity to manipulate canopy architecture with blue earlier on, and probably with much higher doses than we expected. But again, right now for commercial application, we don't really see a lot of opportunity to use blue. But to be clear, we are continuing the research. Okay, next, far red, and this is a big one. So I'm going to try and move efficiently here because there's a lot of content ahead still. So with far red, we hear things like far red is going to somehow enhance yield. And people believe that this could happen through something called the Emerson enhancement effect. And we also hear people say that far red maybe can put the plants to sleep to produce more flowers. The thing with this is that there's like kernel of truths to all of these, but in terms of commercial application in cannabis, that sort of theoretical truth and those kernels of truth that might be true in other species don't seem to apply here. So let me first address this for the first 2 points about far red enhancing yield through the Emerson enhancement effect. One of the first experiments that we did trying to understand this was comparing PAR and EPAR, right? So by definition, PAR stands for photosynthetically active radiation. It's describing wavelengths of light between 400 and 700 nanometers, whereas EPAR, truth be told, I don't know the exact bounds of EPAR, but suffice to say EPAR extends that range to encapsulate far red as technically something that's driving photosynthesis as well. So let me talk you through the bar chart on screen right now from left to right. To be clear, these bars are not representing yield. These bars are representing light intensity treatments. So what you're seeing in the blue color, use my laser pointer. I just realized I was using the pointer and no one could see what I was pointing at. What you see in the blue bar is PAR light between 400 and 700 nanometers, and the red part of the bar is far red light. So what we see here is that in treatment 1, we have 1100 micromoles of PAR light plus 200 micromoles of FAR red. And we compared that treatment versus just the equivalent total flux made of just PAR, right? So here we have a total of 1300 micromoles, and here we have a total of 1300 micromoles. One has FAR red, one doesn't have FAR red. Same thing here. In the next treatment over, we have 1300 micromoles of just PAR light with additional 200 micromoles of FAR red on top. And treatment number 4 is the total sum of photons equivalent to bar number 3. This is comprised of PAR and FAR red. This is comprised of just PAR. And what we saw was that while FAR red didn't inhibit yield, it also didn't significantly enhance yield above and beyond what we were getting with just PAR light. So some people may say, well, what about the Emerson enhancement effect, right? This idea that with FAR red, you can get a yield response greater than the sum of its parts. Little coffee pause for me. It's 7:21 in the morning for me, so thanks for humoring me. I want to talk about the Emerson enhancement effect and how it works, because it is a real thing, but it's the kind of phenomenon that is really interesting in kind of like an academic lab, but not commercially so relevant. To understand the Emerson enhancement effect, we need to look at the light reactions of photosynthesis in some detail. So are these animations going to work for me? Yeah, we just got to back them up. Okay, so starting from the left of your screen, here's how the light reactions of photosynthesis work. Light comes in and excites an antenna complex on photosystem 2. And that photonic energy essentially induces resonance in photosystem 2 that causes a splitting of water. An electron is liberated from water, and that causes hydrogen and oxygen to split in the thylakoid membrane, which is what's down here. That electron that has been taken from water moves through something called an electron transport chain. And that just means there are these protein complexes of increasing electronegativity, meaning they want to pull an electron towards them. But as that electron passes through those complexes, it powers them up for just a little bit. It's like plugging your vacuum into the wall for just a second, and it turns on for just a second. That's kind of what's happening here with these little protein machines. So this electron flows through these machines. In the process, an additional hydrogen proton is pumped into the lumen. That is an energetically demanding process. It can't just happen passively. And then this step right here is interesting. We get to another protein complex called photosystem 1. Just like photosystem 2, photosystem 1 has an antenna complex that receives light energy. But unlike photosystem 2, it is preferentially excited by far red light, right? And that isn't to say that it doesn't get excited by other light as well. But again, just to emphasize, it is preferentially excited by far red. And that could be interesting because this electron, it could move through this protein complex and it could get to ferredoxin and it could do what it does over here, which is produce NADPH and ATP. But it doesn't hurt to give it a little boost. And sure enough, that's what far red can do in this case. It can give it a little boost and make this step of the process happen a little bit faster, a little bit more efficiently. As you can see, that electron is consumed at the production of NADPH, and these two hydrogen protons that were hanging out inside the thylakoid membrane, they'll actually passively move through ATP synthase to produce two molecules of adenosine triphosphate. And I mean, you probably already know this, but ATP and NADPH are like a biochemical form of energy. They're the compounds that get consumed in producing everything else in the plants. Now, the thing is, this middle step that is preferentially energized by far red, again, this can happen with or without far red. You only get like an enhancing effect if you're using a lot of light that isn't PAR over here. I'm sorry, if you're using a lot of light that isn't far red over here, such that you are liberating a lot of electrons from water and you're driving this half of the process really hard and really fast. If you end up with kind of like an energetic bottleneck over here because this part of the process isn't moving fast enough, well, that's a situation where adding more PAR light isn't going to make photosynthesis go faster because you have a bottleneck. That's a scenario where using far red preferentially can help this whole thing work more efficiently. And that is what the Emerson enhancement effect is. As it pertains to commercial cannabis production, again, no one is really getting to the point with their lighting where they're getting a bottleneck here, and they're having photosynthesis slow down. So although it's something that we can induce in a lab or in like a controlled environment kind of academic study, it's not something that I would suggest anyone really worry about for commercial application. It's simply light intensities that are, for a bunch of reasons, not going to be a part of your cultivation style. Okay, so the next thing that we hear about is using phytochrome as a means, I'm sorry, using far red as a means of phytochrome reversion. Um, this is a theory that comes from nature. You know, in nature, as the sun rises and sun sets, the ratio of red and far red light shifts. And that shift is important because in plants, there's a light receptor called phytochrome, which has two different conformational states. Basically, to simplify, it can either be shaped kind of like a horseshoe or it can be shaped opened up like that. Um, Basically, when it's in these two different conformations, it activates different biochemical pathways. And the thing that determines whether it's a horseshoe shape or more of a linear shape is whether it's more exposed to red or far red light. So if you put all that together, you say, well, great. In nature, if that ratio of red and far red is shifting, and I'm therefore changing the activity and the function of phytochrome, that could be a really useful tool, particularly if we know that phytochrome is involved in flowering regulation. Um, Suffice to say, we've done some studies on this. We have tried somewhat emulating sunset in a controlled environment by manipulating that red far red ratio in the last hour of the photo period. And what we have seen is that for the most part, it doesn't do anything, except that we did see one cultivar where emulating this far red sort of sunset effect did significantly enhance yield. But it came at a cost. Yield went up, um, but at the same time, potency went down. So that's the sort of thing where we say, well, that's interesting, and we should certainly tell the story. Um, but it's not something that we would advise people to do commercially yet, because, like I said, this was only in one cultivar, and the actual yield of THC was lower because of how much lower the potency was, even though yield went up. So we see it as an opportunity. We say, okay, well, let's make sure we focus some research on that in the days ahead. And maybe there's something else that we can do to amplify that yield and maintain potency. So stay tuned for that. I think it's an interesting area of research, but again, not something that I would advise people to do en masse in a commercial production. Okay, and lastly, red light. If you've been following any of our webinars, you've probably heard Fluence talk about photobleaching, which is this phenomenon that bleaches the top of your canopy. And by the way, this could also be called white tips. The truth is the underlying mechanism no one quite understands just yet, so we don't have a great name for it. But you've seen this before. And suffice to say, we know that it is induced by the absolute dose of red light, right? And that's important to understand. It is the absolute dose, not the percent of red light, but the absolute dose. We thought maybe we could try and overcome photo bleaching by using some far red. We thought actually that maybe that energetic bottleneck that I described in the light reactions of photosynthesis, we thought maybe that was involved in causing photo bleaching. And if we could alleviate that bottleneck, photo bleaching would go away. Not the case. It actually makes things a little worse. Um, the thing is, though, the reason we're so interested in red is because red photons are cheap to produce, right? And that's why you see so much red used in crops like lettuce and tomato and cucumber and everything else. And if we could break through this sort of red ceiling with cannabis, it would really be a big deal. It would save people a lot of operational costs, particularly in Europe when energy is so expensive. Okay, I'm not going to spend time talking about the light reactions of photosynthesis again. Let's move on. So here is the good news and kind of the punchline that I want to deliver here. Yes, red is cheap to produce, and yes, red can induce white tips or photo bleaching, but it turns out that if you apply it with the right kind of schedule, you apply it when the plant is not so sensitive to these red photons, there is a way with the right recipe that you can achieve about an average OPEX savings of about 19%. right? And that number can go up or down. So if you have cultivars that are not so sensitive to red light, that means you can use more red more frequently, and you'll realize even greater savings. There are cultivars that are going to be more sensitive to red, and you have to use it less frequently. Suffice to say, at this point, we've developed what we believe to be a very, very good recipe for most cultivars out there. That, again, on average, should save you about 19% of your OPEX. And that is what we recommend in the world of dynamic lighting these days, is a dynamic red and white solution where you can attenuate the amount of red based on the cultivars that you have to achieve maximum yields, maximum quality with minimal operational cost. So let me just recap. I'm going to recap, and then I'm going to show you some references, and then I'll pass it off to Sabrina. So in summary, UV, as far as we can tell right now, only damages plants when applied during flower. Early applications of UV may induce systemic changes that lead to greater yields. Blue doesn't upregulate all secondary metabolites, but may have some utility for pigmented cultivars. Far red, when applied during the photoperiod throughout flowering, doesn't enhance yield beyond what you get with par. Emulating sunset with far red can increase yield in select cultivars to the detriment of total THC. Far red doesn't help overcome photobleaching. It makes it a little bit worse. Red induces white tips or photobleaching when applied with too great a flux throughout flower. But red can be strategically dosed throughout the cultivation cycle to maximize yield and minimize operational cost without inducing white tips. And lastly, I always like to close my talks by thanking everyone for their enthusiasm and appreciation of science, because I know there's not enough of it in the world these days, and it's what we believe helps make the world grow smarter. As much as that tagline may seem cheesy to some of you, it's something that we pretty sincerely believe in. So I'm grateful for the attention. And lastly, let me just show you some references, because the research that I presented today was all from Fluence's perspective. Our research that we do at in a more commercial style facility, it's replicated and randomized, and typically our analysis is done, with things like R or JUMP or SAS. It's sometimes our conclusions are a little bit different from what you would see in academia, and that's why I'm showing you these bullets that you can check out on your own. The difference, I think, has to do with intensity. For instance, I'll point you out a couple here, like Willie Avias Contreras or Stina Cataranta. Both of these individuals have published research that showed an upregulation in secondary metabolites with blue light in cannabis, which is interesting, but the research was done at much lower intensities, more around like 480 micromoles per meter square per second, whereas our research is up around 1300 typically. So I'm not going to elaborate on why those differences exist metabolically. There's not time. But if you want to kind of further your education on plant light interactions, I would suggest screenshotting this and having a look at a few of these references. And with that, again, thanks once again for your attention. Now, Dr. Sabrina Carvalho is going to talk about a new technology we have. Go ahead, Sabrina.
Hello, everyone. So I'm here to present to you how we bring this knowledge into our solutions for the future. And especially today, I will talk about our new RAPTR 2. Pressing next, hopefully reacting. Yes. The RAPTR will come in two types of light distribution. It will bring the typical Lambertian shape, but also what we bring up as new is our quarter beam shape. What it's doing is bending the light, and by bending the light, we are allowed to get better uniformities in lower ceilings. So when we have a smaller distance to the crop, then this type of robust light distribution will help us out with that type of facilities. Also, this type of RAPTR has the driver integrated, so making it easier to install. Comes with 3 different types of spectra for the time being. First of all, the very well known and loved BW4. You can see the spectra on the right corner over there, laser pointer, so that I can show you. So this is the typical one that everybody knows. We are also bringing what we call a BW4A, and A as alternative. So what we have is different LEDs equipped this luminaire, brings the same blue, red, and green percentages as BW4, but because it was equipped differently, it allows for becoming a more efficient and smaller heatsink frame. So that it helps us with more efficiency. And our fun LED, I would say, is the T48, what we like to call T48, because it will bring you the capacity to steer your spectra using 2 channels and will allow you to create all the way from 40% red BW4 equivalent type of spectra all the way to 80% red type of spectras. Now, we have set point call for building recipes in 2 ways. One is what we call the foundation using 0 to 10 volt signals. We call them the wireless flex dimming solution because we're bringing this into the wireless communication style as well. We have a transmitter that can control wirelessly the luminaires up to 3 channels. Because T48 has 2 channels, it will be seamlessly operated via this type of transmitters. Each channel individually, so you can control them to build recipes as well. But we also have built a overpower protection. So it allows us to protect the drivers and the equipment to function properly when we are building the recipes without going over the power capabilities of the fixture. We can control up to 200 fixtures with this type of communication and transmitter. Now, next. Yes. We also have a new and advanced solution. This is able to actually connect using an industrial PC and a few equipments available. Using gateways, we can actually control it via our software or via a climate computer. And this capability also allows us to create the recipes via the climate computer or via our own softwares. We also created a new software that allows us to actually, in both the foundation and in this type of advanced solutions, with this app, we can actually tell which fixtures are going to be controlled and create a zone, a control area. So with this, it's easier to commission the way of communication between the fixtures and the gateways or the transmitters. Then what we do have that at least I love and been enjoying a lot is the software. The advanced solutions are powered by the Signify Interact software. So we are able to create our own recipes via the web app, as you can see here in the figure. There you can create your light recipes, your schedules. We can control that via percentages, PPFDs, or to control the spectrum. This can be integrated with your climate computers as well if you want to build it upon your current software. Now, the way it operates. This is more precise than the foundation because the foundation is based on percentages in a 0 to 10 volt way. This is to build precision with, you can see the PPFDs, you can see the percentages of your spectra, the power consumption that your LED is bringing when you're building your recipe. The recipe editor, you can, for us, is the 24-hour. So what do you want to happen in a day? And we build it to a capacity of having 36 set points within your 24 hours. I hope you enjoy the flexibility of that, and that will bring you a lot of capabilities into your system. You can create recipes, and you can create and save up to 100 of those. Then, how do you operate your cycle then? Well, a recipe brings what you want to do in a day. A schedule will help with the next step, which is calling what you want to happen in the cycle. But in this case, for example, when you're building, this is what you see. And here you can see the first step of your recipe in the first part of your day is fading up, and you are building a recipe with about 20% blue, how much green in percentages it has, how much red in percentages it has. You can see here in micromoles per second in this case. If you calibrate the system, you will see it at the plant level. Here, for the sake of explanation and demo, we are just showing the output of what the lamp is showing. So you can see it as output of your lamps in this case, but normally you would see it as where the crop is at. That's why, for example, here, please, this is 2,400 and some micromoles per second. So it's what is coming out of the lamp when I was just demonstrating this buildup. You see the par and the total. The total includes the far red. The modules of T48 do not have far red, but the far red here is accounted for so that you will see also the impact of the other LEDs tail into far red. The white LEDs, for example, often have that, the reds as well. So you will have full control over this. As Dave was saying, the reasons to build within the spectra with the reds and is that it will allow you to avoid the white tips, for example, and build into energy savings. And a good example is that, for example, in this step, I have you can see here, a high percentage of green, a high quantity of green. The next step, I'm building up to more red. And what you see is then that the shift of power. You see that in the first step, you were consuming almost 100, I believe it's 96. And then in this, you're building to a very similar par level, but at a much lower power usage of your luminaire. This allows you as well to have a higher control in checking your HVAC and your energy controls of your facility. So you build a recipe. What next? You can build schedules. So you can actually turn in the software to have a running recipe, so it will constantly do that, but you can also plan what's going to happen in your cycle. So for example, in this case, we would have a 65-day schedule in that particular area, and you're wanting to have something happening in the first 7 days, and then you will have something different here. For example, we are calling the recipe of energy savings for this 40 days here. It can be called, you can recall any type of recipe to any time you want. You can build a schedule up to 365 days. So you can schedule a whole cycle with your needs for your crop. As I said, you have up to 100 recipes that you can save in your library. You can also see about 85 control areas. And here in the main menu normally of this type of software, this is what you see. You see all your control areas, and you will be able to create your schedules, when to start them, when they will finish, and plan all of the schedules within that system. A couple of examples, let's say, of how to operate via our software or the climate computers is, imagine here, for example, that this is a room with 4 quadrants or even 4 rooms that you're operating. These are different control areas. So up to 200 luminaires can be controlled in one control area. You will have those zones for flexibility that you are operating. There you will have different varieties growing, for example. If you're changing a couple of zones where you're building a new variety there, or the rooms are starting with a new variety, you can call the recipe in and start in the different quadrants, as you see here in the design, with that particular recipe. Then another example of how flexible this system is that you build up on different schedules. You have different zones, different control areas at a different time of their schedule. This on your left, for example, is running the recipe that you chose for week number 2, but here, because it's week number 4, is already starting a different recipe. And by week 7, because you have, for example, you selected the different recipe to happen on week 7, this is what is happening here, because this zone is on week 7. This, for example, is very common in what we call perpetual growing, where you can have different zones at different timings, even within the same room. So I hope that with this show up of what we are building as a solution shows you the flexibility, because red can be strategically steered towards your cultivation cycle, and we try to optimize our solutions to get you to the maximum yield while minimizing your operational costs. The RAPTR was designed for a simpler or easier installation in mind. And also we have the 2 channel set points that are able to be controlled via our foundation solution or more advanced solutions, all with the capability of creating recipes. And we can also provide scientifically based recipes for you. And we have Signify Interact now for our more advanced capabilities, and also to connect you to climate computers if you like. I hope you like it. And I think this was my last slide, so we are up for questions indeed.
Thanks, Sabrina. And I've answered a couple questions in the chat while you were presenting.
Cool.
There was one question that I didn't have a great answer for, and I think you might not know the answer either. Someone asked if they can be used outside the greenhouse in the field. And what I had said was that they're designed and intended for indoor, like greenhouse application, but they are sealed.
Well, yeah.
I think the answer is no, though, not in the field, right?
No, they were not designed. Well, I can have an answer for that. They were not designed for open field. They are designed to handle greenhouses and indoor facilities conditions, high humidities and so on, but not full rain. Yeah, we did had once a similar LED to this one installed in open field for sugarcane once, because they really wanted it, but that was not an ideal solution at all. So let's please not.
Okay. I was also asked a question on a separate thread. Just how do you know what the right recipe is when you're programming this thing? Which I think is a pretty good question. So the truth is that probably out of the box, you don't know. Like, you don't 100% factually know this is the perfect recipe for me and it's going to work. What I would suggest is we have what we consider to be kind of like a default proprietary recipe that we recommend based on our research across several cultivars. In that recipe, we dynamically attenuate spectrum and PPFD, depending on developmental stage and what week we're in and so on. And again, based on kind of an average response we see across a lot of cultivars, we think it's a really great starting point that should work for most applications. Having said that, what I would advise every grower to do is dial it in, keep an eye on your crop, right? So start with that default recipe. And by the way that would work is you would get this light and then you would connect with someone on our team to implement that recipe with you. And then you could look at your crop and see how it's responding. And you're saying, you know what, I'm not seeing any kind of stress. Maybe I can actually do a little bit more red, right? You can bump that up and realize a little bit more energy savings, or you'll see a cultivar that's more sensitive and you say, this is not a good solution for this cultivar. You can dial the red back. And we would give you some guidance on kind of the when of your cycle that we think that would be most effective. But I would also call this an emerging technology. in a crop that, again, has great genetic diversity. So over time, more recipes will come to light. And who knows? I mean, maybe there will be a future where people are actually willing to share their recipes and say, this is what I'm doing with this cultivar, and here's what's working, and here's what's not, and so on. But that information is still to come.
Yeah, yeah, I agree. The diversity is so large that the way of seeing it is that we have done the studies to validate a baseline where you start, but you know your crop the best. So from there, you will need to fine tune a bit. And that's why this library of recipes also exists, is that you can start with a baseline and then develop your own tweaks. The moment you have your own dialed in recipe in your library, you just call it into the zones where that variety is, for example. So we built in flexibility for you to be able to do that for the time being. Yes.
Yeah, actually, something I should add too. We don't often talk about this in webinars, but we do offer research as a service. So if you had a cultivar that's really, really important to your business and you say, no, I really want to have an optimized recipe for this cultivar, but I don't have the time and space to figure it out myself, and I don't want to risk my commercial operation, we can work with you to develop that recipe. We would obviously need your genetics, but we can use our growth chambers and our facilities to dial that in with you. Tim, what else have we got? I noticed the Q&A is relatively quiet, which I mean, I think that just means we've delivered
the message is loud and clear. Yes, yes. Yeah, and there still is time to ask your questions, so feel free to drop some in. A question I had is, if I was a grower, can I integrate dynamic lighting into my existing grow, or do I have to go out and replace all my lights? Is it
that's a hard question, right? Because in an existing grow, we obviously don't know what hardware is already in there and what control exists. So my answer off the top of my head is you'd probably have to swap out your lighting hardware. But I say that, I'm sure there's going to be some kind of exception to the rule, so I don't want to just make that broad statement. But I think there are too many ways people are growing to give a simple answer.
Yeah, I agree. It depends on the light. First of all, our software that you see here, it operates our types of lights. So if your lighting solution that you have currently is not ours, then it's going to be more difficult. But if your climate computer is integrating all of that, indeed, it's just integrating this type of lighting. So it really depends. The other aspect that it depends is the software we have. For example, if you are integrating this type of software into your controls, if your spectra is a fixed spectra, it will only be able to dim it up and down because the spectra is not changing. That is a fixed system. It only has an amount of white LEDs, red LEDs, and so on. The tunability of whites, reds, and so on is brought to you via the T48 that we are just launching. So the dynamic aspect of red changing, green changing, and so on is with the new lamp that we just launched with the dynamic tunable solution. The fixed spectral ones can be controlled with the dimming, and the software will function fine with that indeed. So it depends. So in doubt, contact us, ask. We will tell you how far we can go with the extra steps that you might need with your solution.
Excellent. So somebody asked the question in chat. We answered it, but I just want to make sure everybody knows that as an attendee here in our webinar today, you will get emailed a copy of this presentation, or a link to it, I should say. And typically it takes us about a week to post on YouTube. So this will be available within the next week or so on YouTube, and you'll likely see our social media team drop in links to that when it's available. So be on the lookout for that. Dave, Sabrina, if folks here want to learn more about dynamic lighting, what should they do? Should they reach out to you guys, or?
They can reach out to us. They can check out our YouTube channel. If you just search for Fluence Cannabis Lighting on YouTube, you'll get there. I'm relatively active on LinkedIn, where I talk about photobiology and upcoming events and so on. We do a lot of scientific communications at conferences, and not just me, of course, Sabrina also does. I say relatively, I'm not really a social media enthusiast. So for me, if I post a write up about photobiology every couple months, that's a lot. I'm not the daily posting kind of guy, and I don't use a lot of Instagram and things like that. But Sabrina, what's the best way for them to reach out and learn from you?
Email, LinkedIn for sure. I'll be, for example, in Dortmund in a couple of days for the CB Expo, PTMC in Portugal the week after. So check us out on LinkedIn. We normally tell you as well where we are going to visit you guys. And yeah, but definitely I would say if you send me an email, quite often I will see it faster there than I would see my phone. So yes. Email is the
Okay.
fastest way to get on track with me. So reach
I see
out
one
because
person.
then we will put it forward to whoever can help you out.
Yeah, I see someone in the audience has their hand raised. Probably the easiest thing is if you can put your question in the chat, we can better address it there.
Yeah.
Or
And
not the
while the
chat, I'm sorry, the Q&A section.
Q&A. Yeah. And as that person hopefully types their question in that area, a couple of questions just came in last minute here. James asks, what's the minimum height above the canopy that the fixtures you were speaking about, Sabrina, can be installed? Like, what's the size of that footprint?
We have a whole rules set up and whatnot, but often enough we advise at least 30 centimeters away from the crop, bare minimum, to guarantee some uniformity. But it's counterintuitive. Huh? The further away from the crop you are, the better we will get at having the least amount of lamps in a room to get you to the highest uniformity. It sounds counterintuitive. We keep hammering on that. Distances are key to get you the lowest amount of lamps with the highest intensity uniformly spread over the room. This bending allows us to have a really good uniformity at 1 meter away from your crop easily. There is indeed the Sergio, if you can, you type your question, would be great. Because we can only see what is written.
Yeah.
Yeah, and someone was asking if we have tested far red at low light intensities in the ranges of 600 to 800 ppfd ranges. We have tested far red in many, many ways.
Yeah,
In
so
more
actually
ways
that's
than we would love to
Sabrina, maybe you can elaborate
avoid.
on this because, yeah, Jaime asked that question. And I mentioned in Fluence's program, we have done it a lot of ways, but in terms of just like essentially flowering time and so on, he asked if we looked at lower total PPFDs, like 6 to 800. And in terms of that kind of application that I think he's asking about, we haven't done that at Fluence, but maybe in Phillips's history, you've done some of that?
Well, checking onset of flowering, we tried to check that out, but it's not easy with all the varieties. But lower intensities as a total, I hope that, yes, total 600, 800, 1,000, like you were mentioning, even over. We've tested far red in that, and we actually, some of these results are even published. Like Wageningen University, there was a student that did that, and all the work was done within the 600 and 1,000 range. And far red is just that love-hate relationship of we don't see much happening to justify the prices of it at all. So yeah, go check it.
Okay, and with that, I know we're 1 minute away from the top of the hour, so we got to wrap up
Yes.
there.
Yeah.
Here it is, our contact information. If you'd like to learn more,
Oh, yeah.
don't hesitate to reach out. We're always happy to talk science. And with that,
Yes.
thanks everyone for your time and have an excellent day.
Thank you. Bye-bye.